45, and find the field pattern for that. You know, the far field pattern in the XY plane, if they're isotropic radiators. That kind of stuff I used to do, but I think it's more valuable for students to sometimes come up with their own project that they're interested in, something that would be of interest to you. Follow me? Now, I'll send out more specifics after class today, but if you could, give me these proposals this week, and the last day of class, I'll expect them to be handed in, okay? And you need to provide the MATLAB code, plots, and a brief write-up. It doesn't have to be anything extensive, but give me the details of what you did, why you did it, and really how you did it, okay? Second, now we're going to the answer. Does anybody have any questions before us? All right, did you look at what I posted up there? It's fairly interesting, but it's complicated. So it needs your attention. I'm going to go ahead and take you through the reason we're doing it. We're going to see this. So last time I came down and I showed you how to extract coefficients using derivatives. Do y'all remember that? Now this time I'm going to go through the whole 9 yards here and get to the point where you'll be able to estimate the worst case EMC or signal strength for a standard trapezoidal pulse. And this is something for any component. I'll take you through the problems. I'll make sure you understand this. Okay? So pay close attention to this, because this is not in the textbook and it gets a bit confusing. We're going to start with a standard waveform. This is going to be a repetitive square wave, but it's actually trapezoidal wave. And so forth. This is going to be the axis of time. This is going to be some V of t, just a voltage signal. It's going to have a peak magnitude of A. Now, here's some things you have to be aware of, and this is in the information I posted. The rise time here is specified tau rise. The fall time here is tau fall. But you always take the shortest of these and equate tau rise equal to tau fall. In the real world, that is about true. Y'all with me on that? And the next thing they do is the width that we call tau is actually measured from the points. This would be tau. Tau is measured from the point where the first waveform is about half, it goes to A over 2, half is, and it comes down at that point where tau fall over 2. You're going to basically, that width is the important width. Y'all follow me, class? Then we have the standard period here, capital T. In radar, this is called a PRI, pulse repetition interval, but it means period. That's all it is. And it's repetitive over there. So that's our waveform. Now, what happens, and I'm only going to take one pulse and do it on this side. I know that this waveform, since it is repetitive, has a width tau, height A, this is B of t, and as rise time equal fall time, it's periodic. I can say that this is actually, it can be estimated in terms of Fourier series, which would be the C of A to the J in omega naught t, where n goes from minus infinity to infinity. Here, omega naught is 2 pi f naught. F naught is considered the period, so it's really 2 pi over t of the fundamental. F naught would be the fundamental frequency. It's the lowest frequency that would be repetitive. In this case, you simply take 1 over the period t, and that would be equal to f naught, or t is equal to 1 over f naught. Y'all follow me? You're familiar with harmonics, right? So that's a Fourier series, and C of n here, again, would be equal to 1 over the period, the integral. Typically, you go from minus tau over 2 to tau over 2. It has to be, t over 2. It has to be over a complete period, but it doesn't matter where you start and where you end, just over a complete period. And that's V of t, times e to the minus j n omega naught t dt. That's the event for this. So the next step, how many actually took a look at those notes I posted? All right, if you looked at them, you saw something like this in the makings, right? And he goes through the whole 9 yards in the proof. So now I take the first derivative of this. When I take the first derivative, I get my v prime here at t. And what do I actually get? Well, if you take a derivative with respect to time, it's the slope of the line, isn't it? All right, for this one, the rise is a, the width is tau rise. So here, it's going to have a height of a over tau rise here. And it's going to be a square wave until it hits this point. Then it goes to 0. Y'all with me? All right, the height of that is a over tau rise. It's going to stay that way until I hit this point. And at that point, it's going to go down. It was high, it goes low, so there's a negative slope of the same amount. Now it goes down to minus a over tau rise. It stays that way until this point, and then it goes to 0 and it repeats. And the width of these things are just tau rise. Y'all agree with that? All right. That means over here, when I take a derivative of this series, now I have v prime of t equal to my summation of Cn, and it's really going to be Cn prime e to the j n omega naught t, where n goes from minus infinity to infinity. And the thing is, that Cn prime, if you just go up here and take a derivative, you see C of n prime is actually just C of n times j n omega naught. So the actual C of n I want is simply equal to C of n prime over j n omega naught. Now that's the whole key to this, is taking derivatives until you get impulse functions, and then get the Fourier series coefficients for that impulse series, and you backstep your way to the actual value of C of n. Keep watching and you'll see. Are you with me so far? At least what I'm doing. Now I take another derivative of this, and this is the axis time. And when I take that derivative, I get this. Now, what's the derivative of a u of t function? Because this is what this looks like. It's a delta function, right? Integral of a u of t is rand. It's a delta function. So it's the slope of the line goes from nothing to a value. It's a delta function. Usually delta functions are just defined, or they're really identified as simply a pointed arrow up. And the weight, or the magnitude of the delta function in this case would be a over tau rise. At this point, it goes from that high point, a over tau rise, to 0. So that's a negative slope of the same magnitude. It's minus a over tau rise. It's going to stay there until I hit this point. Then there's another negative jump. Following, it goes from 0 down to minus a over tau rise. So it's a negative delta function here. Same magnitude. And then finally over here, it goes up to really a over tau rise. It's the same actual height, a over tau rise. And it repeats itself. Now that chose a series, so now I have v double prime of t is equal to my summation from n equals minus infinity to infinity of C of n double prime e to the j n omega naught t. And here that C of n double prime is equal to the actual value of C of n prime divided by j n omega naught squared. And it's also equal to C of n double prime is equal to 1 over t. Now here's the real magic of this thing. This right here is a Fourier series. Do you all agree with that? First it's periodic, so it can be represented by a Fourier series. That coefficient C of n prime mathematically is defined as 1 over the period, the integral from minus infinity to infinity of the value of that functional form, v double prime of t times e to the j n omega naught t dt. But that functional form for the second derivative are all delta functions. With me on that, guys? Now I'm going to come back here. I'll let you catch up, and I'm going to complete this. This is done in, it's done in the notes I posted. So when I take a look at C of n double of t, this is the second one, that's 1 over the period, integral or minus t over 2 to t over 2, or over any period. It could go from 0 to t, it could go from any place, but typically it's done this way because the pulse actually starts at 0, and you don't want to start the integration where there's an actual discontinuity. You always want to start integration where there's clean space, you might say, where it's 0. So now I define the actual function that I'm going to do. My v double prime of t is this. Those are all impulse functions, and they all have the same magnitude. So now I put my a over tau rise here, and then I put my first delta function is just delta t. Remember, a delta function goes to infinity when its argument goes to 0. So that first one turns on at t equals 0. Do y'all see that, class? The next delta function turns on, but it's got a negative sign at t minus tau rise. Y'all follow me on that? Make t equal to tau rise, bang, that one comes on, and it's negative. Y'all see it from there. Second one's negative right there. The next one happens at what? It's a minus 2 minus delta of t minus, and then it's going to be tau rise plus tau. Finally,
wouldn't it be tau minus tau rise? Because you're.
Wait a second here. Oh, no, it's just tau. Because look, if you remember, this is the half point. So if you slide it down, it's actually tau. My bad. Follow me? Remember, this is from the half point. So if you take this and slide it back, this is where it actually occurs. Do y'all see that, class? That's where the actual transition.
Okay.
Then finally, it goes up at delta of t plus tau rise. Now I have to multiply that by e to the jn omega naught t dt. And those are my C of n double prime. It's worth noting one thing about the delta function, just so everybody remembers it. If you integrate a delta function of delta of t minus any constant a, or it doesn't really matter, f of t dt, what that actually does is this thing never has a value other than 0 until it is exactly equal to a. Y'all follow me? At that point, the integration of the delta function has a magnitude of 1. This is just evaluated at the point A. So this is simply f of A. Y'all remember doing this class? It's called a sampling or an extraction method of the delta function, where you can extract information by setting that where it turns on. So that means when I evaluate this, my C of n double prime will have a magnitude of A over T tau rise. Now, when I integrate this delta function, delta T times this one turns on where, class? At 0, and that means I evaluate e to the jn omega naught times 0, or e to the 0, which is 1. Y'all follow me? So this is going to be 1. The next one turns on at tau rise. So now I'm going to have e to the minus jn omega naught tau rise. The next one turns on at tau, so now I have minus e to the minus jn omega naught times tau. And the final one goes up, and it turns on at e to the jn omega naught, and it's really going to be tau plus tau rise. And that is my constant right there. Now this takes a little doing, but I'm going to show you something. Let me expand this part here just for a second. When I have, so you'll be able to see it. I'm going to do this over here. when I take a look at this, I have 1 minus e to the minus j and omega naught tau rise. Then I have, the next one is minus e to the minus j and omega naught tau plus e to, then I'll break it up, j and omega naught tau right there. And it's times e to the minus, or plus, no, sorry, that should be a minus, e to the minus j n omega naught tau rise. Now, what I'm going to do is factor out 1 minus e to the minus j n omega naught tau rise out of here. When I do that, I get a 1, right? And then if I take a look at this,
How come you have 4 exponential functions there?
there's 1, 2. I broke, no, this is times, it's
Oh,
it's
okay.
this.
Oh, I see.
I just multiplied it when it break
I
out.
got you, yeah.
So it's going to be that one, and then I get 1. Then I have 1 minus e to the minus. And this will be 1 minus e to the minus j n omega naught tau. Now, if you just take a look at this and do the math, you'll see it. 1 times 1 gives me 1. Then I have e to the minus j n omega naught tau rise times 1. That's this one. And then I'm going to have minus e to the minus j n omega naught tau. So that's this one right here. Tau. That's this. And then I have the final one, which is these two times each other. The negatives result in positive. Y'all follow me on that, class? So this is the factoring. Now keep watching, because here's where it gets interesting. When I have that factor as such, remember that's just tau, and that's just, I mean, this is tau rise, and that's tau. Now I'm going to go ahead and pull out the front here, and e to the minus j n omega naught times tau rise over 2. Let me do it this way. I'll do it over here, so you can see it. I want to put it up high. I'm going to pull out an e to the minus j n omega naught tau rise over 2. And then I get e to the plus j n omega naught tau rise over 2 minus e to the minus j n omega naught tau rise over 2. And then on the other one, I'll pull out an e to the minus j n omega naught tau over 2. And I get e to the plus j n omega naught tau over 2 minus e to the minus j n omega naught tau over 2. The only thing I'm doing is I'm working on this, and I'm trying not, what I'm trying not to do is just rewrite this over and over again until we get it to the form we need it. Y'all follow me? So that's what that series is, but if you look carefully there, as the makings of 2 sine functions. I want to show you what I mean by that. You know, when you have sine of any function, that's really e to the j theta minus e to the minus j theta over 2j. Y'all remember that? It's Euler's identity. It's one of the ones you have to know, especially if you go into communications. Now I can just multiply by 2j on that side. And now I have the actual core functional exponentials. I have what this is in terms of a sine, and I have what this is in terms of a sine. So I'm going to combine these 2 outer terms, and I get e to the minus j n omega naught, and that's going to be tau rise plus tau over 2. And you can just leave it, that's just a phase term. Then on this term, I have 2j times the sine, this is the sine, of n omega naught tau rise over 2 times another sine of n omega naught tau over 2. And actually another 2j, so I'll just square that. And that is what this series becomes. Do you appreciate that? This is in the notes I put up. It's a clearly defined proof. How many remember seeing this, by the way? Anybody? When they looked at the notes? You did? Okay. All right. This is what's coming. So now I take that information and I replace this series right here. Y'all follow? Because what we've just done is we created something that's at least common to us, something we understand with two sine functions. Y'all follow me? So now I come over here, and for the sake of time, I'm just going to erase this, and I'll put that in there. So now I have really the phase term, e to the minus j n omega naught quantity tau rise plus tau over 2. That's just the phase term times first sine term, sine of n omega naught tau over 2 times the second one, sine of n omega naught tau rise over 2. And that's my C of n double prime. This is in the notes, if you look, it's, that I posted, it's clear, very clear. So now I really want I should say this is C of n. I want my value of C of n, so I take what I just got, C of n double prime, and I divide it by j n omega naught squared. So I take this, and I divide it by j n omega naught squared. Because I took two derivatives to get that. Yeah.
What happens to the 2j squared when you move it over there?
This, so, I'm sorry, you're right. I need to put that over here. 2j. I would have seen that in a second because of what I'm about to do. You're absolutely right. 2j squared has to be. All right, now, the next part of this is I need the fit. I'm gonna define this in terms of the sinc function. And remember, when you talk about sine of x over x, that is the sinc function. Sinc of x. Do you remember that, everyone? How many at least remember seeing it? Okay. Now, what does that actually look like in magnitude versus x? Well, we take the magnitude of sine of x over x versus x. At 0, to calculate it, you need to do L'Hopital's rule. Take the derivative of the top is cosine x, derivative of the bottom is 1. Then evaluate the cosine x at 0, which is 1. So it's 1 there. Then it goes to a 0. First 0 is when the sine is 0. Sine of x is 0, which is at pi. And then at 2 pi, and so forth. And it's symmetric. It looks like this. Y'all remember seeing something like that? That's a typical sinc signature in the frequency domain for any kind of a pulse waveform. So when I take a look at this, I want to get these things in terms of sinc functions. So what I'll do is take this and I'll spread it out. I'll make it 2 jn omega naughts. Then what I'll do is divide top and bottom by 2j squared. So this gets divided by 2j. This gets divided by 2j. Right here. Y'all follow me? Now, after that, I'll take tau rise and I'll put it here. Well, actually, let me put tau there, tau rise here. And then I'll multiply this by tau and divide by tau as well. So this becomes simply divided by tau. Why don't you say the only thing I'm doing here is adjusting it so I can pull out a couple of sinc functions. Y'all follow me? This is a coefficient. That's a phase term. Now, if you look carefully, you see how I have sine of n omega naught tau over 2, and then the j's cancel, don't they? You see how you got j and j here? They divide out. So I have n omega naught over 2 tau. N omega naught, sorry. Times, my bad. Tau and tau rise. I'm sorry about that. I have n omega naught tau over 2 and n omega naught tau over 2 right here. And then I have n omega naught tau rise over 2, n omega naught tau rise over 2 here. So that means this thing turns into, for C of n, actually, I just divide by 10. So this isn't C of n double prime. This is the C of n I want. It's going to be A over tau rise, and then it's going to be, excuse me, tau rise got pulled in, not over tau rise, A times, and then it's going to be tau over T, which is the duty cycle. And then you get the phase terms, e to the minus j n omega naught tau plus tau rise over 2. And then you get a couple of sinc functions, which are the key. Sinc n omega naught, move that over up there. It's going to be times the sinc of n omega naught tau over 2 times the sinc of n omega naught tau rise over 2. And that is C of n. And this right here becomes critical. So that's C of n. With me on this so far. Now for a little bit more information on this. Now I'm going to have to do it over here so you can see what I'm doing. What we care about is the magnitude of that value C of n and the frequency of it. And there's one other thing we have to do before we can get to the final format that we're going to use at the time. So if I look at this, when I talk about first the sinc of n omega naught tau over 2, or better yet, even just talk about this sine x over x. Well, if you look at sine x over x, it's equal to about 1 for x much less than 0. If you think about this, or it's less than 0. And the magnitude of that is about equal to 1 over x, just the magnitude. It's actually not, it's repetitive, for x greater than 1. Now what I'm really going to tell you is this: if you plotted out the magnitude of the sine of x over x, just the magnitude, what you'll see is you'll get something like this. And this would be a log plot, so this would be the log of the frequency, or log of x, log of x, here. And this would simply be equal to 20 times the log of the magnitude of sine of x over x. And the point that starts going down is when really the value of x is going to be 1 over, I'm sorry, that would be pi over 4 radians, pi over 4, but I'll talk more about that in a second. Anyway, this would be an envelope. Now the true value of this would be something that would go like this. Sorry. It would look like this. You would have this, maybe one other number, and then you would have this. It would be periodic where it would go up and down, up and down, up and down. But this would be the envelope maximum. Do you all see that right there? The 1 over x value would be maximum. Maximum value. Now, try to appreciate I'm doing this before I do the next part and show you how this thing actually, the value of Cn is actually shown. But what they're really worried about when you're doing EMC analysis is the worst case EMC. By the way, what I'm showing you here is it's in the note set. I really don't like using PowerPoints when I teach. I think sometimes they just hypnotize people or mesmerize and they just fade out sometimes. So try to stick with the board here. If you take a look at this, and the first thing I'm going to do is get rid of omega, and I'm going to let omega naught be equal to 2 pi f naught. And if that's the case, then I get C of n is equal to Matter of fact, let's do magnitude of C of n. A times tau over T, period. Then, it's the magnitude, I don't worry about that term right there. Magnitude of the sink. Now it's n omega naught tau over 2, so I really have n times omega naught is 2 pi times f naught times tau over 2. Then it's times the sink function, magnitude of the sink function of n omega naught, n times 2 pi f naught tau, but it's tau rise over 2. Alright, I'm just showing you the magnitude of this before I plot this. Now you can see, I went to f naught because usually these things are done in frequency domain in terms of hertz, not radians when they do this. But you can see the 2's cancel. So I have pi f naught there. 2's cancel here. And I have n pi. And that's n pi right there. Remember, those are 2 sink functions, right? So, here's the part where you kind of have to pay attention. Now, you realize you're going to have values for this for every value of n. N equals 0 would be the DC value, you might say. N equals 1 is first harmonic, n equals 2 second harmonic, n equals 3 third harmonic. Y'all follow me on that? And you would get single values in the frequency domain. But the way this is usually talked about is they're going to let n f naught become equal to f. So now instead of going at discrete frequencies, we're going to actually show what this looks like as over the frequency domain, where instead of nf naught, those would be discrete values, we're going to have it as a continuous variable. We're going to plot it. And we're going to plot the envelope of this thing. All right, so just stay with me. It won't be as bad as you think. When you look at this, they'll put the log of f here. They're going to do a Bodie plot, where now this is going to be 20 times the log of the magnitude of C of n versus that. So in the beginning, remember, when f is like, if you're a very low frequency, the sink functions themselves are 1. You all follow me on that? So in the argument in here, I'm going to go ahead and change it. I'll go ahead and get rid of the n f naught, and I'll just make this simply pi times f times tau. And this is going to be pi f times tau rise. Here. So at low values, the only thing you have is this. So it means you would have a value here that would be, well, actually make it go up higher. Value up here of 20 times the log of the magnitude of A times tau over 2. Then you would keep going. And the first, and I use the term break frequencies, is when this is equal to pi. So when you take a look at pi f tau equal to pi, that means that argument is 0. It would be at a 0. Y'all follow me on that? The sign of, because the same function is sine of x over x. So when the sign is at pi, it's a 0. Y'all follow me? But this is called the first break frequency. So if you take a look at this, the pi's cancel, and you get f is equal to 1 over tau. That's the point where it starts coming down at a rate of minus 20 dB per decade. Are you with me? Just get this plot down. This isn't important. That's the first breakdown. Where this is at 1 over pi times, actually, I said that wrong. They do it this way, and I didn't say this right. When I have the sine of 1 over 1, that's the first break frequency that they use. If you get that, that means the F is gonna be 1/pi tau rise. Or tau, just tau. So this is gonna be pi tau. This is in the book, this is the first break frequency. It's gonna keep going down to 20 dB per decade until the next one turns on, this one. And that occurs at a break frequency of 1/pi tau rise. Then it starts falling at minus 40 dBs per decade. Now that's what you need to know. After all this, when we have a standard square wave that has a rise time and a fall time, the ultimate thing that happens when we analyze this in the frequency domain, we want the worst case behavior. So what we do is we take a look at the envelope of these coefficients, C of n, because we know that those things are the thing that weighs the frequency domain components of either a cosine series or an exponential series. And I'll get to the cosine series in a second, but just keep this in mind. This is important to remember, to at least appreciate. And I'll show you how this works with the problem. The next thing we have to do, and there's a lot to do, is we have to take the standard exponential series, double exponential, and turn it into a single-sided cosine series. So this is the next part. And I think I posted this information too. It's gonna seem kind of too much going on until you see how the problems are done, and you'll appreciate it. I'll say this, I'll probably say it a lot more, many more times, but when we're actually, when you do EMC analysis, you look for worst case always. It's how bad can it get? So the envelope I just showed you is as bad as it can get for the value of C of n. There's actually a lot of points where it goes to 0 and less than. But you're always looking for the worst case type of effect. And this is the worst case. So next thing I'm going to do is take that exponential series and turn it into a cosine series. The reason for this is because now it becomes exactly analogous to the phasor form of voltages. You know how when you have like 10 times cosine omega t plus 40 degrees, and you did circuit analysis, because it's a periodic function, you just took the 10 and you put it at an angle of 45. You remember that? You completely ignore the omega t when you do circuit analysis problems, right? You didn't have a cosine form there. Then you analyze it in the frequency domain, and then once you get the answer of current or voltage, you take that back to the time. And it's going to be the same way for us when we do EMC analysis. So now I have to get those cosine coefficients so we can take it to a phasor form. You'll see this. So when I have any kind of function v of t, and I say this can be approximated by c of n e to the j n omega naught t from n equals minus infinity to infinity. What I can do here is say, and also I'll make one other point, that because c of n is equal to 1 over t, integral from minus t over 2 to t over 2, I don't even have to go that far back. C of n has a magnitude value of c of n, and it's at a phase, or it's at some e to the angle of c of n, right there. C of n conjugate is really equal to same c of n magnitude e to the minus j angle of c of n. Y'all with me on that? I'm doing this because I'm going to need this information to be used there. That's conjugated. And if you look at this right here, this can be expressed as a series. It goes from n equals minus infinity to 0 of c of n e to the j n omega naught t plus a summation from n goes from 0 to, or actually, how about not 0, how about minus 1, and I'll start at plus 1 of c of n e to the j n omega naught t from n equals 1 to infinity plus some c0. And c0 is just going to be the DC value of the function v of t. That's the average value. Remember anything about Fourier series, you remember, you always had that coefficient, the first coefficient that represents the DC value. Okay, now I come down here and I start manipulating this thing to get what I want. Remember, C of n here has a magnitude and an angle. Well, you want to just watch, I'll tell you the final formula right now. So that becomes just a magnitude of C of n and an angle e to the, I'm going to have to erase it. This is really going to be magnitude of C of n e to the j angle of C of n, and then it's going to be times e to the j n omega naught t as such. And this one's the same thing, it's going to have a magnitude of C of n e to the j n omega naught t. Now, instead of going from minus infinity to 1, I'll go from -1 to minus infinity. And then the next step is the key that you at least appreciate. If I decide to go from n equals +1 to positive infinity, wherever there's an n in here, I'd have to make it negative. You all follow me? I'd have to put a negative sign. It's the same exact thing. But if I went from +1 to infinity, then this would have to have a negative sign. And I'm trying to do that for you.
What has the negative sign?
Because I've changed, before it was -1 to minus infinity. It's the same thing as going from 1 to infinity. Wherever there was an n, make it a negative n. Put a negative sign for it. So then it's going to be the magnitude here of C of, and it would be -10, which is the same thing as C of n, times e to the minus j phase angle of C of n, times the e to the, then it would be minus j n omega naught t. It's getting a little cramped here, but in the note set, this is clear, it's clearly shown. Now, the next thing I'm going to do is this. I can see that I have, well, if you look at cosine of theta, that's equal to e to the j theta plus e to the minus j theta over 2. You all agree with that, class? All right, so I'll multiply this by 2. And now, if you look here with this series business, just watch what I do. The sum is over the same range. So now I can say that this is equal to the summation. The C of n magnitude is the same, C of minus n is the same as C plus n. So I can take the magnitude of C of n out. Here my n goes from 1 to infinity. And then I have these terms. I have e, I'll put this one first, to the plus j n omega naught, and it's going to be I have that twice. This should be the phase angle. Plus e to the minus j angle of C of n times e to the j n minus j omega naught t. And I actually can put that C of n inside here. I can get rid of that j here and just put plus as such, and I can get rid of that minus there and just put the C of n in there. Minus j n omega naught t plus angle of C of n. Now the reason I've done that is if you look at this, the n omega naught t plus the angle of C of n, that fits this form perfectly. If you equate that to theta, you can see you get a 2 cosine. So now what happens is, this doubly-sided exponential series that used to start at minus infinity and end at infinity can be expressed without error as simply the magnitude from n equals 1 to infinity of 2 times magnitude of c of n times the cosine of n omega naught t plus the phase angle of c of n. And that's the beauty of this. The value of c of n is still given the way it was prior, that c of n is equal to 1 over t, the integral from minus t over 2 to t over 2 of v of t times e to the j and omega naught t dt. That's still the same. The value of c of n, so it's the same, but now I have it with these cosine, the cosine form in there. Now please realize the fundamental reason we want to get that form is this: that when you had circuit theory back in the day, and you had something like 10 times cosine omega t plus 30 degrees, and you had a resistor and an inductor, and you were after the current, I t. The only thing you did is take this and turn it into a phasor, 10 at an angle of 30 degrees volts. And then you made the inductor simply have an impedance of j omega L, right? And then you solve for the current, looking at this thing as a complex number, dividing it by R plus j omega L, and you could get the current, right? Then you could go back and get the time domain form of that too. All right, now, with this one here, what was omega naught t at 30 degrees is really going to be n omega naught. So for any given frequency, right, I can go ahead and say I really have a magnitude of 2 times magnitude of c of n at an angle of c of n, and I can find the response of the circuit to that. And then the next one, and the next one, the next one, and simply assemble the output as a superposition of those things. Do y'all follow me on this, class?
So what do you say? How does the having the n in there change it versus?
Well, n omega naught would be replaced. The coefficient here of omega,
Yeah.
now is n omega naught. So the impedance of this would be j n omega naught times L, and you would have to calculate a different impedance for each different frequency. But I'm going to get to that in a second.
Okay.
Now, after all that is said and done, we're going to go back to this value here. And we're going to talk about that plot. I know this always seems a little much at first, but it'll be all right. Trust me on this. So, next. What I want to do is just take a look at the magnitude of this. Remember, what we really are going to do is, for this one too, we're going to replace n omega naught, we're going to replace that, really we're going to replace omega naught by 2 pi f. Well, we don't have to, but I'll say more about that later. What we really care about is this coefficient, what it looks like in a frequency domain. So normally they do a Bode plot of this, and they'll take 20 times the log of the magnitude of c of n here, and actually it's 2c of n, because this coefficient, this is the cosine series, has a coefficient of 2c of n, and they'll plot it versus the log of f. Now, for the standard trapezoidal wave that we just saw where we have this, and this is tau. This is tau rise. This is tau fall. And this is the period t. We find that has the form of c of n. I erased it, but I'll put it down here. As the form c of n is equal to a times tau over t times the sink of really pi f tau times the sink of happens is what was n omega naught got replaced by 2 pi times f naught, and then you let n f naught become f. And so this is just the envelope of the worst case stuff. When we look at this, you're going to have this value right here will be simply 20 times the log of the magnitude of 2 times a times tau over 2. It's this coefficient right here. Let me just do this for you. If you take 20 times the log of c of n, right here, 20 times the log of magnitude of c of n times 2, you're going to get simply the first term, which is going to be 20 times the log of 2a tau over 2, over t, plus 20 times the log of, and then it's going to be the magnitude of the first sinc function, sinc of f pi, or f tau, pi f tau, plus 20 times the log of the second one, which is magnitude of sinc of pi f tau rise. So when you're plotting these things, this sinc function for low values of f, the sinc of 0 is 1, that's 1, so the log of 1 is 0, so nothing happens until you hit this first break frequency right here. Write this down too. This frequency is going to be 1 over pi tau. Then this waveform starts falling down at a rate of minus 20 dB per decade. And it hits the second break frequency. This is f low, call it f high, which is going to be 1 over pi tau rise. And then it starts falling down at minus 40 dB per decade. And that's the envelope, this C of n, that is the coefficient of this stuff right here. Just appreciate that for a second. That's the important one right there. Remember, that's t. And there is a value of 2 there. So, now, my next step is to actually show you how this is used for a real problem. And then it'll start making a lot more sense. And I'll pull a problem up. A couple of problems, but I want to actually do this. I may post something right now too. One, yeah, about 15 minutes. So it doesn't. That envelope right there becomes the key to analyzing circuitry. So I have multiple displays, so I have to get just this. Alright, this is what I was talking about. So, alright. See this right there? That's what we just did, right? This is the important one. So that's what I was doing on the board, getting it down to these sin x, these two sync functions right here. And then at the end of the day, it becomes that right there. Can you all see this right here? My cursor. It became that. And then we took it and turned it into this cosine series. I hope you can see this. And the actual coefficient of that cosine series is 2 times the actual C of n we calculated for the exponential series, and it's this. Then this is what I was trying to show you. Sin x over x is 1 for small, and the magnitude of sin x over x is bounded by 1 over x for x large. And this is what I was trying to show you when I had the actual, it's flat, or sin x over x would be flat until the first breakpoint, which is at 1. And then it starts coming down at minus 20 dB per decade. But we care about the envelope. Even though the sine function is going to have, go to 0 and go back up to 1, we care about this envelope. Now for the next part. So if you can see, this has the basic waveform shape I showed you before. I mean, the envelope right there, it's up there. And now, at this from 321. It says a 10 megahertz clock has an oscillator that goes from 0 to 5 volts with rise time with 20 nanoseconds fall. With rise falls times 20 nanoseconds and a 50% duty cycle, and it's connected to a system. You have a resistor and a capacitor, two capacitors that are in parallel, 50 picofarad and 20 picofarad. Obtain or determine the level of the 11th harmonic at the gate terminal. So I'm going to show you how to do this one, and I'm going to do it over here, but I'm going to leave it on the board so you can see this. So for this one, the value of A was 5 volts. Y'all see that? Next, he gives you a fundamental frequency of 10 megahertz. That means the period is simply 1 over 10 megahertz. Y'all follow me on that, class? That's the repetitive period, megahertz. So it's equal to, this is 10 to the 7th, this would be 10 to the minus 7th. Next, he says the duty cycle is 50%. That means tau, the on time over the period, would be 1/2. And if you look at that, that means tau itself is simply 10 to the minus 7 over 2, or it's 5 times 10 to the minus 8. Y'all follow me on that? That's 50 nanoseconds. Agreed, everyone? After that, he says that tau rise is equal to, in this case, is it 20 nanoseconds? Right?
Yeah.
20 nanoseconds. You all see this? Okay, these are the specifics. He wants the level of the 11th harmonic right here. And the circuit is simply, the circuit we're analyzing is, we have a source right here, plus the minus source, and it's actually a clock right here, and that would be V and T. Then you have a resistance of, what is it, 100 ohms, and you have two capacitors that are in parallel, so you can add them together, 50 and 20 picofarads, so 70 picofarads. And he wants the value of the 11th harmonic here. So he wants V out of really 11 F naught. We're going to get that. Can you all follow me what I'm doing? All right. First thing I do is, with this information, I sketched what's going on. I'll do it over here. So I start with the magnitude is going to be 20 times the log of 2 times C of N, or C, I'm sorry, 2 times A times tau over 2, tau over T, the duty cycle. And actually, I better say this too. Usually what they do is get the output in dB microvolts. So what they normally do, if you're doing an output in dB microvolts, you have to do is this. I'm trying to shoehorn this in here. This output is actually going to be 20 times the log of the magnitude, and then it would be 2C of N, but it would be divided by 10 to the minus 6. So this output would be in dB microvolts versus log F. Now, just go with me on this one. I know that it starts right here, and this value, where it's going to start, is going to be 20 times the log of the magnitude of 2C of N, or 2 times A times tau over T. I'm going to stop for a second and just mention this. The tau over T is the duty cycle. Do y'all follow me? Because it's 50%, that 2 and that tau would go away. So it's just going to be this right here, and I'm going to go ahead and put the 10 to the minus 6th here. So this is where it would start. And it's going to maintain, it's going to maintain that value until the first break frequency. And the first break frequency is 1 over pi times 1 over pi, and tau on this one was equal to 50 nanoseconds, so it's or 5 times 10 dB. So it's 1 over pi, and it's 5 times 10 to the minus 8. So that will be the first frequency. We'll get that in a second. Then the second frequency that breaks that is 1 over pi tau rise, and that's going to be 20 nanoseconds, 10 to the minus 9. So it's going to come. It's going to come flatten and start coming down at 20 here, and then it's going to come down to 40 dB here. Until we get to the 11th harmonic, so we have to find 11 F naught here in a second. Can you all follow me how I'm doing this? I'm trying to get the level. This is supposed to be a flat line here. That level is just this, so it's going to be 20 times log of 5 over 10 to the minus 6. You with me on that? It stays at that value. This would be the source value until I hit the first break frequency, which is going to be 1 over pi tau, which is 1 over pi, 5 times 10 to the minus 8. You're going to give me these frequencies? This is about 133 dB microvolts a day. If you do 5 over 10 to the minus 6, and then take the log of it, that's log base 10 times 20. I think it's about 133.
133.98.
All right, so this comes in at 133.98 dB microvolts right here. And what's this first frequency here? 1 over pi times 5 times 10 minus 8 megahertz, sure.
6.37 megahertz.
And where's the second break frequency? Which would be 1 over pi 20 nanoseconds. Or 2 times 10 minus
1.59 times 10 or
15.
15.9.
Megahertz, right? Correct?
Mm-hmm.
Okay, so that's what we're dealing with now. The 11th harmonic is where we have to analyze it. The 11th harmonic is, if the fundamental is 10 megahertz, the 11th would be 110 megahertz. Do y'all follow me on that? This is the harmonic frequency. You multiply that by whatever harmonic you're looking for the output at. They said the 11th, right? So the 11th times this. So we really need the value of this coefficient at the 11th harmonic, which is out there at, just call it F naught times 11, which is going to be 110 megahertz, way out beyond the first and second break frequencies. Follow me, everybody? So here's how we go about it. First, we're going to find the signal strength at that frequency. Here's how you do it. If you give me another minute and a half, 2 minutes, I know I'm going to go over, but I'd like to finish this thought so you can see what's going on. Once you see it, it's easy. But until you see it, you're wondering, why in the world are we doing all this? I know the feeling. I have it all the time. So now, we're going to get the magnitude of the value of really the coefficient that cosine sees. So at that 11th harmonic. So it's the magnitude of C of n plus, you might call it, at 11 F naught. Here's how we do it. We start with the magnitude that it came in at DC, and that, I mean at low frequency. So that was 133.97? 98 dB. All right, and this is all in dB microvolts, so I'll just put this in dB microvolts. 98. Now, hear me on this one. To account for this drop, remember it's 20 dB per decade. What we do is we're going to find out how far down. If it went 1 decade, if we take 6.37 to here, if it was 1 decade, then it would go down exactly 10 dB or 20 dB. You all follow me? If it was 2 decades, it would go down 40 dB, right? A decade is the frequency range. So the way you get it for anything in between that, start with the actual fall off rate, which is minus 20 dB per decade. You all with me? Then you take the log of the frequency you end at, divided by the frequency you begin at. I started here, I ended at 15.9. So it's the ratio of the two. It's the log of the upper frequency, 15.9, over the lower frequency, which is 6.37 megahertz. The megahertz cancel, you don't need to put it down. With me? Now I'm right here, please just be attentive to this. Now it starts falling at 40 dB per decade. So now I put a 40 up there. I'm sorry. Yeah. You put a minus 40, there's a couple ways to do this, but this is the easiest. Now you put the log of where did it land at, 110 megahertz, over where did you start at? Well, that was at 15.9 megahertz. Y'all with me? That will give me the value in dB microvolts of this coefficient way out here. This is important. So this is what, if we talk about the 11th harmonics signal strength value in dB microvolts, this is what it is. Can you give that to me? And I really appreciate you just hanging with me for a second. I'm a few minutes over, but guys, if anybody has to go somewhere, just leave. But I want to finish this thought today. I don't want to have to reiterate some of this. What did you get?
92.44.
44 dB microvolts. Can anybody confirm that? Just
Give me a second.
I want to make sure we didn't do something. Because now we're almost done.
Yeah, that's right.
Okay. Now we're going to find the actual value of the output right here. And here's how we do it. First, we think about what that output would be if we knew the 11th harmonic here, its value, not in dB microvolts, but in volts, all right? So to do this, when we would get V out, if I wanted V out here, it would simply be V in, or V source, or what do we call that? VC, for clock. VC, and it would be times, at the 11th harmonic, times the output impedance. The output impedance would be simply 1 over J omega C, right? Over the sum of, but this omega will actually be, would be J times 2 pi F naught times 11. In other words, it would have to be at the 11th harmonic. You're going to evaluate this impedance. Times the capacitance, which is 70, or I'll just put C here. I know it's going to be 70 picofarad. Then it would be divided by 1 over J times 2 pi F naught times 11C plus the resistance. And let me come over here. I'll just show you this. So when I get this transfer function, I get V out is equal to V clock times, and I know I have 1 over J omega C over 1 over J omega C plus R. This is the form it has, but normally what you do is multiply top and bottom by J omega C. So you get V out is equal to V clock times, and this is the transfer function, which would be simply 1 over 1 plus J omega R times C. Can you all follow me on that one? I took the transfer function, I just made it into something that's a little easier to deal with. That omega would be 2 pi times F naught times 11. So now, when I have this transfer function that I showed you there, and I go ahead and I take 20 times the log of V out over 10 to the minus 6, because it's dB microvolts, I get 20 times the log of this clock right here, of the magnitude of V clock over 10 to the minus 6, which I've already done over there, and it's going to be plus 20 times the log of this transfer function, which is 1 over 1 plus J times 2 pi F naught times 11C. And when I figure out what that term is, I'll add it to what I just found before. Remember, I found the value out here. Did I erase that? No. The actual output value of the source, the source value, pardon me, that the 11th harmonic is at. Do you all remember how we got that? We used that interpretation right over there, correct? Now, I have to add this to it. So if you can be so good, and I appreciate it, go ahead and find out what this is. It's 1 over the magnitude of this. So what we actually need is the value of 20 times the log of magnitude 1 over, and you have to take the square root of 1 plus, and this is going to be 2 pi times 10. It's actually going to be just 110 megahertz times 2 pi. So it's 2 pi times 110 times 10 to the 6. And then it's going to be times C. And C is 20 or is 70 picofarads. 70 times 10 to the minus 12. And you have to square that. But I need this. If you can give it. This constant is
10
2.
to the 6, 70, 10 to the negative 12.
You get 2 pi times 110 times 10 to the 6 times 70 times 10 to the minus 12. Once you get that value, square it and add 1 to it. And then take the square root. Take 1 over times the log of that. I'm going to finish this problem.
Negative 0.010.
For the whole thing? This whole thing is minus,
Yeah, that's what I got.
minus, say it again.
Negative 0.010.
Yeah, that's what they got too.
Well, somewhere, let me take a look at this for a second. Oh, times R. I didn't put R in there. So what I need to do is take this times 100 and square it, my bad. Try that.
Negative 13.88.
That sounds about right. Now look, minus 13.88, right? Add that, minus 13.88 to 92.44.
78.56.
You're gonna notice something. This is what we got, right? That is the envelope. The exact solution is 73.95 if you actually took into account the sinc function's variation, but they only worry about worst case, 78.56. That's how you do the CMC problem. But the real thing about it is I had to go a long way to get it. You need this plot for the trapezoidal waves to get an estimate of what the signal strength value is. To have an envelope of the signal strength value, whatever harmonic you want. And then to evaluate the final thing, you have to get the transfer function evaluated at that frequency. Take 20 times the log of that transfer function and add it to the prior result. In this case, it's a subtraction. And you get the output. Now, that's the same for all these problems you're going to see. Same exact setup, the same thought process. And I appreciate you staying with me. Give me an extra 10 minutes. I owe that to you somehow. I'll make it up here. You'll get some of these problems, but if I'm going to do one thing for you guys, I'm going to give you some. This is real world stuff. When you go to NASA or wherever you work, or Intel or anything like that, if you get involved with any of this high frequency stuff, design and analysis, this is the way to do it. It's not just bandwidth disease. Hey, if you need to, does anybody need to test? I brought up now this morning.